Okay, so how is everyone today? Good, I hope? All right. So today is the what? 11th? Yeah. 11th. All right, so then last time we sort of wrapped up, for the time being, we've wrapped up our discussion of radicals and fractional exponents and things like that. And then we went on, pardon me, to talking about polynomial terms and polynomials. So just to briefly remind you what that was about. So a polynomial term, there's sort of two categories. Is that we can have the constant variety, so constant. They just look like this, a, just some number there. And then, you know, an example would be something like just 8. And then we have the non-constant variety, so non-constant. Would be something that looks like this, a multiplied by x to exponent n, and an example could be something like negative 3.71 times x to 23, say. So something like that. So, you know, that's a polynomial term, that's a polynomial term. The requirements on these is that this should be a real, and it's constant, and it is non-zero. Okay, similarly for that a right there. And then x is a real variable. And so what I mean by real variable is that when you see a term like that, you can think of x as like a placeholder where you're going to plug in a value. So like you could plug in 2, or you can plug in 2.7, or what have you. So that's a place where you're going to plug something in. That's what I mean by a real variable. The kind of thing that you plug in has to be real. And then this exponent here, what must be true about it? It has to be a natural. So in particular, it has to be positive. So constant and positive. You know, so that means that concerning the exponent, it could be 1, 2, 3, 32, 48 million or whatever. But it's not permitted that the exponent should be something like 2.1 or half or a third or negative. Okay, and then a polynomial is just the sum of polynomial terms. All right. Any question about that? So one of the themes of the class is going to be that we're going to talk about polynomials. We just love them because more or less the reason why we're going to, by we, I suppose I mean mathematicians. I can't necessarily include you in there. Mathematicians love polynomials because everything you can do with an integer, you can do with a polynomial. So like, you can add, subtract, and multiply integers, and you're always going to get another integer. Same with polynomials. Another thing you can do with integers is you can factor them. Like 6 is 2 times 3. We're going to want to do that with polynomials. And another thing you can do with integers is you can divide them in the sense of quotient and remainder. So like, if we were to say, take 1,314 and divide it by 100, then the quotient would be 13. You can get 13 100s out of there. And when you've taken those 13 100s, 14 are left over, and you can't get any more. So you'd say that the quotient is 13 and the remainder is 14. Okay, and we're going to want to do the same thing with polynomials. But for now, I'll remind you of this of FOIL. So FOIL. So that's this formula. So A plus B multiply C plus D. So we've already done it, so I'm not going to rederive it. But just to remind you of the way that this works, is that, looking at it from sort of a global point of view, you can sort of see that it's, well, it's this thing multiplied by that thing. So it's the product of two things. And the strategy for figuring out what FOIL should be is that, well, let's just say that they're both sort of like boxes, and we're going to give ourselves permission to look inside of one of the boxes. So I'll look inside of the box on the left. It doesn't matter. It could have been the other one. But so whatever this is being multiplied by that. And inside of there you can see, oh, look, there's two terms, A and B. So the way multiplication works is that we're going to distribute this to the B and also to the A. So we're going to make a distribution. So distribute. So you get a box, right? And you get a box, whatever's in there. And then you do that, and then you look at it and say, oh, I could do two more distributions and commute some things and do some other math operations. And in the end, there's going to be 4 terms. And we named those terms F, O, I, and L from where they came from in here. So the F term is AC, the O term AD, the I term BC, and the L term BD. Okay. So now, how many terms are there? 4, right? Corresponding to the letters F, O, I, and L. Then if you look at a particular term, say that one, then you can see that term has 2 bits, 2 parts to it, an A and a D. And those aren't called terms. Rather, the parts of that are called what? Starts with F. Ends with actor. Factor, right? So then this has 2 factors, right? A and D. So 4 terms, and then each term has 2 factors. All right, so that's FOIL. Now, so I'm going to make sort of a dividing line here and say, okay, here's the next formula. So we've already done this formula also. So A plus B, and now we're going to square it. So I'm going to write equal, and then I'm going to give myself a box to write the answer in. Okay, so we're gonna figure it out, and we're going to use FOIL to do it. Now, the most common wrong answer is to say that the answer is A squared plus B squared. That's the most common wrong answer. Okay, now why is that wrong?
Just another way of writing the one above, A plus B times A plus B.
Okay, so I agree entirely that that's how we should go about it. So I'll say it like this. So we have inside of the parentheses we have 2 things. We've got an A and a B, and the way they're being combined is with plus. Now suppose that I obscure that so that you can't see what's in there. And then I say, well, if it looked like this and I'm hiding what that operation is so you can't see it, what would be necessary so that it really is A squared thing B squared? Multiply. If it was multiply, it really would be A squared plus B squared. It really would be. But it's add. So I agree entirely with what you said, that this is really just, because it's squared, it's saying make 2 copies of this thing and multiply them, and it'll be an instance of FOIL. So A plus B multiply A plus B. And so now it's just like that. So now we use FOIL. So, using F, O, I, and L, what's the F term going to be? A squared. The O term? AB. The I term? AB. So sort of strictly speaking, it should be BA. But multiplication commutes, right? So I'm just going to go ahead and do that. So AB again, and then plus B squared. So you can see we got 4 terms, FOIL. And concerning these, because it's A plus B and then another A plus B, I'll say that concerning these 4 terms, the first and the last, the A squared and the B squared, are pure in the sense that this one only has A's and that one has only B's. And the ones in the middle are mixed in the sense that this one has A's and B's and that one also has A's and B's. And we can simplify this to get the answer. It is A squared plus twice AB plus B squared. So the most common wrong answer when asked A plus B all squared is in a sense that student leaves off that bit in the middle. And some of y'all basically said that. I asked, if student responded with A squared plus B squared, then what would be wrong? I think I heard one of you say something like they left the stuff off in the middle. Okay. But those things can't be left off. Any question about this one? All right, so next formula. And now I'll ask about, instead of A plus B all squared, I'll do A minus B all squared and write myself a box to write the answer in. And I'd like for you to do basically exactly what we just did above to figure out what it should be. All right, so in exactly the same kind of way, the most common, probably the most common wrong answer that I ever see to this is A squared minus B squared. That's probably the most common wrong answer because exponent does not distribute over subtraction. Okay, but we can do this and say that this is A minus B and then multiplied by another A minus B and then use FOIL. The F term would be A squared. Then what's the O term? Minus AB. And then another minus AB. And then what's the L term? Plus B squared. Now why plus?
Because we're multiplying negative and negative cancel each other out.
Very good. So again, do you observe that the first and last terms are pure in the sense that this one has only A's, this one only B's, and the ones in the middle are mixed in the sense that they both have A's and B's? So then we can, simplify this to this: A squared minus twice AB plus B squared. So notice that these formulas are really similar. The only distinction is that this one is saying plus twice AB, and this one is saying minus twice AB. They both have positive A squared and positive B squared. Okay. Now, so what I'd like for you to view this formula as is that it's like we took A plus B and we took another A plus B. So A plus B and then another one. And then this one is like we took A minus B and then another one. So this last formula I'm going to write is I'm going to say, well, let's take one of these and one of those. What I mean is that what about this one? A plus B multiplied by A minus B. And again, I'll give myself a box to write the answer in. And in the same way that we figured out the answer, I'd like for you to figure out the answer. So again, in the FOIL terminology, product of, we'll use FOIL to carry it out. What's the F term? A squared. The O term? Minus AB. The I term? Plus AB. And then the L term? Minus B squared. And again, now we have minus B squared because one of them is plus B and the other minus B. Now, just like the previous two times that we did it, we've got the first and the last are pure in the sense this one has only A's and that one only B's, and the ones in the middle are mixed in the sense that they have both A's and B's. But now something is notably different. So what happens to the mixed ones? They cancel, right? So that the result is A squared minus B squared. So notably, this one has no mixed terms. So that was notable enough. That's a notable enough circumstance that we used it last time, Friday, I guess, because the context that we used it in was we wanted to rationalize a denominator. We wanted, given a fraction that had square roots in the denominator, we wanted to achieve a situation where there were no square roots. So the first one that we looked at was a little bit easy. You just had to have the idea that, oh, you need to multiply by 1, but you have to sort of, pick wisely. And we had to multiply by something like the square root of 7 over the square root of 7 or something like that. Then, we tried a different one. We found another one. It was a little more challenging, and sort of the thing that you might first attempt doesn't work. And we needed this one more idea that had to do with these. So this expression, these two expressions, A plus B and A minus B, that's a notable enough circumstance that we just take that plus and make it a minus, or take that minus and make it a plus. That's a notable enough circumstances that concerning these we say that they are blank to each other. Conjugate, right? So they're conjugate to each other. And the purpose of the conjugacy thing is that when you multiply two conjugates, there's no mixed terms. There's no AB. So the problem, stating the problem on Friday, is that, we tried to multiply by 1 in some circumstance, but because we didn't use the conjugate thingy, we ended up with mixed. We couldn't squash all the square roots. Okay. So this is notable enough to sort of have a phrase, and that is that the product of conjugates, is difference of squares. Difference. So, in this case, those two are conjugates, and you're computing their product. And then that term right there, A squared, is a square, and that's a square. And difference is a synonym for subtraction. So, this issue that the product of conjugates is the difference of squares is going to come up 3 or 4 different times throughout the rest of the semester. Any question about it? All right, so now let's use these formulas a couple times before we move to the next thing. So first, something simple. So how about x plus 7, square that. So now on the one hand, you could just ignore those formulas that we wrote on the previous page and just use FOIL. And there's nothing wrong with that. So by all means. But I'm gonna use that formula on the previous page. And I'm gonna write first thing squared plus twice first thing multiplied by second thing, and then plus second thing squared. So that's just directly substituting in the bits from the previous page, and it's it's typical to sort of do that simplification in your head, right? 2 times 7, that's 14. That's not that not that big of a deal. Something like that. Any question about that one? All right. So what I mean to say is that you know, if you were given this one, say x minus 9 squared like that, it would you know, it'd be totally normal for you to just more or less in one line write the answer. Just so would you please? All right, so then, you know, x squared, and then subtract how much x? 18, right? And then plus 81. And in the FOIL sense, you could say, well, I'm going to subtract 9x, and then I'm going to subtract 9x again for the O term and the I term. All right? Now, beware that sometimes it messes up. So I'm gonna do this one now, and I'm gonna make an error. So if you're gonna copy what I'm gonna write, you know, please note that at least at first I'm gonna make an error. So then y squared minus plus 2y, and then plus 4. So this is a really common error that I find. So on the one hand, you know, what's wrong about this?
It's not, sorry, it's not 2y plus 2y, it's just 2y.
Right. So, you know, the y squared is, you know, there should be 3 terms in the answer. That one's good, first one's good, last one's good, middle one's not good. Should be 4y, currently it says 2y. Now, you know, I can't read minds, but I always try, when I have the opportunity, I ask students, you know, what happened when you did this. In the end, the mechanism seems to be this, is that the formula is a squared plus twice ab plus b squared. So in some sense, that's the formula. And then when you try to do it in your head, essentially what appears to be happening to students who make this kind of error, that one, what seems to be happening is something like this, where they say, okay, this will be y squared, and then plus twice, and then the first thing times the second thing, and then they look at that and say, okay, I got a y, and then 2, wait, did I already have a 2? I don't know, blah, I don't know, something, and then, you know, I don't know what happens. There's like a hesitation there because there's a 2 in the formula, but also a 2 in the input. So can you see it? I just mentioned that because I see, you know, some baseline percentage of students, like 5 or 10% of students, do this. All right, so then, you know, this 2, there's a 2 that belongs right there also. So, you know, y squared plus 4y plus 4. All right, how about this one? 3z subtract 5 squared. All right, so I'll write down something that is initially incorrect again. So then it'll be first thing squared, and then I can see subtract. So subtract twice first thing, second thing, and then add second thing squared. All right. So what's wrong with this?
Just find 3z by 3z, get 9b squared. Oh, okay, never mind.
It's not, the way I'm looking at it, it's not technically, but well, I mean, you need to actually do a lot of operations in both the middle and the end part, but you also did not put it as if they want 3 to be squared.
Okay. So I think we're all hovering around the right idea. So now I'm gonna move work a little bit further forward, and now I'm gonna say this. So I'm gonna go ahead and simplify this, because 2 times 3 is 6 times 5 is 30. So then this would be subtract 30z, and then plus 25, like that. And now I'm gonna write something that still doesn't make make it okay. So now, if you were to respond to this prompt with this work, you'd probably get about half credit. So if it was like out of 10, I'd take 5. Now, why? This one is kind of a hard, it's kind of hard to understand and then accept. So like this line right here, this is correct. But
But you would need to have parentheses on that top line of over 3z.
Is that from here to here, that's just multiplying out constants. That really is 30z, and then here to here, that 5 squared really is 25. Okay, but then here to here, I suppose student is saying that I needed to square the 3. Okay, then why don't you need to square the 9? If that means square the 3, then doesn't this mean square the 9? It would have to. But the thing is that right here, there's 3 symbols, 3z and 2. And there's 2 operations. There's multiply and exponent. This exponent applies to what? Just the z. This exponent does not apply to the 3. Why not? Okay, so we could say it like this. You could say, well, if I ask a different question, how could I make it apply to the z? I could put parentheses. So I'll put the parentheses. But now I'm just going to ask the question again and say, okay, this thing, I want to write it in red. This right here, 3z squared, which being sort of overly verbose, I could say 3z squared. Like that, right? So what I'm saying is that that squaring only applies to the z. Why does it only apply to the z and not the 3? I'm fishing for a phrase that starts with O. Which one? The order of operations, right? The order of operations. That exponent applies first. So what that means, what this means, it means this. Only the z is being squared. If you intend for the 3z to be squared, you must put those parentheses. If you don't put those parentheses, effectively what that means is you're not following the order of operations. Any question about it? All right. Do I want to do any others? Times it. No, we're good. So no questions about this? All right. Now, we want to, I'll say it like this. So I'll call this remark expand and factor. So we can take any one of those formulas, FOIL, or any one of them. So I'm just going to take FOIL, just for, so I can write one down. So A plus B multiply C plus D. And then the FOIL formula is that this should be AC plus AD plus BC plus BD. So now, when I give you a prompt like this, and you respond with an answer like that, which is to say that sort of the direction is that way, the direction of work is pointing that way, this is called expand. But if I prompt you with something like this, and I want you to respond with something like that, then the name of that is factor. So, you know, I could say something like expand 2 multiplied by 3. Well, then the answer is 6. And if I was to say, well, factor 6, then the answer is 2 multiplied by 3. So these things undo each other, expand and factor. And, you know, there's just like many things in real life that sort of, you know, a do and an undo kind of thing. One of them is usually easier than the other. Like walking downhill is easier than walking uphill. And digging a hole generally is more difficult than just pushing that dirt back in the hole. Same thing here. Expanding is what we've been doing, and it's generally easier than undoing that, which is called factoring. Okay, but you know, factoring is something we have to do. So first example. So the request will be, please factor out the greatest common factor. Factor. And that's you know, usually written down as the initialism GCF. And here's the request. So 6 x squared y squared w cubed plus how about 54 x cubed y squared, like that, and then subtract 21 x y cubed w cubed. All right. Factor out the greatest common factor. So I'll give you a second to copy that down and make sure it's written correctly. Okay, so let's look at this crazy thing we've got written here. Well, how many terms are there? There's 3 terms. Because remember, terms are the things that are written that are separated by pluses and minuses. So, you know, there's a term, a term, a term. And then concerning each term, we can look at it and ask, how many factors does it have? So how about that one in the middle? How many factors? 3. And this one over here? 4. Okay. And then now overall, concerning this, I'll note that there's sort of like 4 different categories of factors. There's factors that are like integers, right? Like numbers, 6, 54, 21. So that's like one kind of thing. And then I see that there's some x's in here and in here and there. I see y's and I see w's. So, you know, just as like a checklist, I'll put it over here. I'll say like we've got numbers. We've got x's, y's, and w's, sort of like 4 categories of things. And what we want to do is we want to get as factor stuff out. And I'm going to, since this is the first example, I'm going to do this in a really tedious, slow-mo kind of way. And I'm not saying I expect you to do it this way. We'll do some examples on the next page that show how I expect you to do it. I'm doing it in this slow way because this is the first time. All right. So because we have sort of 4 categories of things, number, x's, y's, and w's, we're going to consider them one at a time. So just concerning the numbers, meaning this 6, 54, and 21, is there an integer that is common to all 3 of them, a factor? 3 is common to all of them, right? Because 3 is a factor of 6, and it's a factor of 54, and it's a factor of 21. All right? So as a result, we should be able to say that this is 3 multiplied by something. And, what we need to do is we need to say, we write the 3 there, and then now we need to fill that in. So in the notes, I'm going to leave that there in case you come back and look and try to remember what it was we were saying. And now I'm going to say, all right. So we're going to factor out that 3, and then inside of the parentheses, we're going to need 3 terms corresponding to these 3. So just concerning that term right there, if you factor out a 3, then what do you need to write? 2, and then the rest of that stuff, right? Because we didn't mess with any of the rest of it. So it would be 2 x squared y squared w cubed, just concerning that first one. Okay, then now plus. Concerning the term in the middle, if you factor a 3 out, then what do you need to write? 18. And then what? X cubed y squared, because we didn't mess with any of that either. So x cubed y squared. All right, and then subtract. So if we factor 3 out of that last term, what do we need to write? 7. And then the rest of that stuff, because we didn't mess with any of it. Is there any question how we got that? Now, the way that you can check that this is correct is by noting that, well, we've got 3 multiplied by a bunch of terms like that. So we could distribute the 3, right? We could say you get a 3, you get a 3, you get a 3. And if we were to do that, if we said, you get a 3, then what would we get if we gave it a 3? We get that, right? And if we said, you get a 3, then what will we get? That one. And you get a 3. That one. Okay. Fine. So now I'd like for you to observe concerning the numbers in front. We've got 2 and 18 and 7. Is there any other numbers that can come out? But wait, I see 2 and 18. But 7, right? So then 2 is common to 2 and 18, but it's not common to all of 2, 18, and 7. All right, so we can't get any more number to come out. So what I'm saying is that in some sense we can check that off the list. Right? Check. Now I'm going to move on to the x's. So concerning these terms, I observe that, remember that x squared, that means xx. So, that's just a nice short way to write xx. There's 2 of them there. And then here, that is xxx. So there's 3 of them there. And then here we have just 1 of them. And what I'm saying is that we want to factor out some x. And the principle is that you look at all the terms and you count up how many x's are available. The choosing principle is weakest link. The phrase weakest link, comes from like the literal physical object, a chain, right? Which is you know, literally like little loops of metal, you know, that are linked. And you know, you're supposed to be able to lift and pull things with chains and what have you. Whichever one of those chains, whichever one of those links is the weakest one, that determines how strong the chain is, right? Doesn't matter if all of if you know 99 of the links are you know He-Man or whatever links. If one of them is weaker than all those, that's the one that actually determines the behavior. So, you know, 2 available, 3 available, 1 available. So how many can come out? 1. 1 can come out. So then doing that, we want to factor out a 3x. You know, so you know, this least one is the winner. That's the winner. All right. So then doing that, now we want to write this down. So this first term, that 2 would still be there because we didn't do anything about that. But how about that? Just regular x, just one of them, right? And then we didn't mess with the y squared, with the y's at all, or the w's. So those are unchanged. Now concerning this, what do I need to write for this term?
18x squared y squared.
Very good. So 18 x squared y squared. So, you know, the reason why x squared is because, in a sense, you know, this term right here, before we factored an x out, it's like it had 3 x's, you know, 3 apples. And then it ate 1 apple, right? And then now it has 2 apples. Okay. And then subtract. Subtract what? Very good. 7y cubed w cubed. Now, having a look in here, you know, the point was that we wanted to get as much x out as possible. But just a quick glance inside of the parentheses there, I can see that there's still x's in there. You know, I see x's right there. Is that okay? Okay, why is it okay? Right, you know, because this one has 1x to currently has 1x to give. This one would have 2. But that one doesn't have any, right? So can you see that, oh yeah, it's the exact same reason as when I asked about 2 and 18 and 7. And I said, oh, but 2 and 18. And then you said something like, but 7, right? Same story here. Fine. So now considering the y's, this term has 2 y's to give. This term has 2 y's to give. This term 3. So which one wins? 2's. So that means that we can say that this is 3xy squared. And then doing that, this first term would then become 2x and then what? W squared, right? Because we consumed all the y's doing that. And then plus 18. Yes?
Sorry. We lost a w at some point.
Did I?
In the second and the third.
Okay. W.
No, I mean going down to the columns. The first term has w3, then w3, then w2.
Oh, yeah. 3, 3, 2. Look at that. Okay. So I'll write that in green. I'm not sure that'll show up real good, but formerly I had miscopied that as a 2. And now it's a 3. 2, 2, 2. 3, 3, 3. Okay. Now am I good?
The bottom one.
The bottom one. Okay. Thank you. All right. Okay. So then I was factoring out a y squared. Okay. So now this would be x squared and then no y's, and then subtract. Okay. So how about this one? Okay. Good. So 7 y w cubed. So any question about that one? So, you know, we wanted to get out all the y's possible. There's still y's in the parentheses, but, you know, there's not enough to for all of them to give 1. Now, how about the w's? Now this one has 3 to give. This one, how many w's does this one have to give? None. And then there's 3 here. So who's the winner?
0.
This is the winner. So now, here's the deal, is that each of these, this one, this one, this one, and this one, are all called common factors. But this one has the nice property that, notice, we can't get any more integer stuff to come out. We can't get any more x's to come out, any more y's to come out, any more w's to come out. This is it. We've sort of like reached the end of the rabbit hole. And as a result, this one is referred to as the GCF. Greatest common factor. All right. So now we need just a couple little permutations on this theme so that you can comprehend the homework. So here's a typical one. So I could say something like 6 x squared y to half subtract 10 x y to 3/4. So now the new element here is, in some sense, just that now we have fractions. Okay, so the easy bit is the integer bit and the x bit. So I'm just going to do that now and say that we could get 2x to come out. 2x could come out, and then we'd have 3x y to half. And then subtract 5, no x's because that went, and then y to 3/4. Okay, so no more integer stuff can come out. And then concerning the y's, here we have half and 3/4. And the rule is still weakest link. So, you know, who is least? Half is. So that's the winner. So that's what comes out. So 2x y to half multiplied by 3x, that y to half went out, and then subtract 5 multiplied by, now, how much y remains? 1/4, right? 1/4. Now why 1/4? Yeah, you're just subtracting. Yeah. All right. So now here's the last one to make sure you don't, you don't become really unhappy at the homework. So how about 15 and then 2w plus 3 to exponent, say, 5. Then we'll say z squared. Add 25, 2w plus 3 to exponent 2, z to 17. All right, so now, again, there's two sort of easy bits on this. The numbers are easy enough. 5 is the best we can do, and then concerning the z's, we can get z squared out. It's the last bit that sort of causes a problem sometimes. So 5z squared, and then doing that, we'd have 3, 2w plus 3 to exponent 5. We took the z squared, and then plus 5, 2w plus 3 squared, and we took 2 z's, so z to 15. So the number and the z's are normal. But then, you know, many times students look at the 2w plus 3 in there and just have like a moment's pause, like, oh, I couldn't possibly imagine. But here's the deal. The way all this works, the only thing that matters is it's the same thing, right? We have z squared and z to 17. So the question is, in some sense, here's 17 apples and here's 2 apples. Okay. What I want you to observe is that, do you see that 2w plus 3 is in both places? So if I just cover this up and call it banana, then here we've got banana to exponent 5, and this one has a banana to exponent 2. So then how many can come out? 2. the only thing that is, that you have to be brave about is to understand that the only thing that matters is that they're the same. That's the only thing that matters. So I'll write down the answer, and then we'll be done. So 5z squared, and then we said 2w plus 3 squared is what can come out. And then it would be 3 multiplied by 2w plus 3 cubed, and then plus 5. We took all of those. Z to 15. Okay, very good. I hope you have